So this is my Friday tropical, intraseasonal, and uh, low frequency background state map discussion held every few Fridays at the University at Albany. I am Paul Roundy, and I'm joined by some students who are participating in the conversation today. And occasionally we'll take comments or questions from the students and sometimes their own input. Uh, we begin the discussion with representation of the large-scale tropical basic state of sea surface temperature patterns. And it's always a good idea to start with the total because the seasonally evolving sea surface temperature structure is important as well as the anomaly. So we're looking here at this is a daily representation of satellite sea surface temperature measurements. And we're looking at the distribution of the warmest waters in the world. The warmest water is presently situated near the dateline. We're going to look at the anomaly in a few moments and show that this is absolutely warm as well as anomalously warm. And that this time of year, oftentimes the warmest water is situated up here, and then over the next few weeks across the seasonal cycle, that warm water migrates down and becomes centered on the equator. But this year, the warmest water is centered right here in the vicinity of the dateline. We've got a well-defined cold tongue here over the eastern Pacific. It's associated with upwelling of cold water from the trade winds across this area. This cold tongue I'll show is also a little bit anomalously strong. So we've got kind of an unusual situation where the East Pacific is cool and the Central Pacific is warm. So it takes on some El Nino characteristics and some La Nina characteristics at the same time. The Indian Ocean this time of the year is typically cooler than the Central and Western, especially the Western Pacific Ocean, because over the last several months, the monsoon has enhanced the wind flow across the basin, leading to wind evaporation feedback and upwelling in some areas, right here, and sometimes over here, depending on the strength of the trade winds. There's a region of seasonally warm water near the coast of Mexico. Notice how the Atlantic region is absolutely cooler than the East Pacific and the Central Pacific regions. And we can come back down and look at the anomalies now. This was a daily estimate. Obviously, if you take a weekly mean, it's going to be a smoother but more accurate representation, but oftentimes I'm going to toggle back and forth between the daily data and the weekly data in order to see how things are trending in different regions. So this is from the Esrael website at NOAA Boulder. And you can come down on the same site and it'll provide the same daily versus weekly anomaly products. So here's the daily anomaly product. And we'll see then basically what I presented before, that it's anomalously cool right along the equator in the eastern Pacific. So it's like a slight La Nina signal going on over there right now. But the central Pacific is anomalously warm. This is consistent with what we'd expect during a Central Pacific structure El Nino event. I have never accepted the argument that El Nino comes in two kinds. Like many people would say that El Nino is either Central Pacific or East Pacific. But reality shows that El Nino events can be anywhere in between, and over the lifetime of an individual event, it can evolve from one into the other and even back again. So it can be misleading to try to represent a whole El Nino event as if it were structured following a particular pattern. But the warm structures in the Central Pacific versus the East Pacific have different average outcomes. And so it's, even though I don't believe that El Nino is well represented by describing it as one, Central Pacific or East Pacific, there it is usefulness in looking at the extremes because they inform us about what the large-scale atmospheric patterns tend to look like during those different structures. But this is actually kind of unusual this time of the year to see a warm anomaly like this simultaneous with a cold anomaly out here. How we normally trace El Nino is by this Nino 3.4 region over here. And right now it's slightly cool. And so you might label this signal as a neutral event. But if you just look at the average of all neutral events by that Nino 3.4 measure, you're going to end up collectivizing events that are quite different from each other. Sometimes neutral events are more mechanistically like El Nino, other times more like La Nina, because of the structures, how convection is distributed, where the warm water is actually located. So it's always a good idea, instead of looking at those indexes alone, to get a picture of what the full global tropical pattern looks like. So in this case, the dominant signal is not going to be the cold water over here, because that's close to normal and it rarely rains in this region of the world this time of the year. Anyway, so there isn't much of a loss of rain rates going on right here in comparison with normal for this time of the year. Normally the intertropical convergence zone, where the most of the tropical rainfall out here is occurring, is north of the equator, and it's actually anomalously warm up there. So this region of the world is a net source of momentum into the middle latitudes, not what you'd think of as consistent with a La Nina situation. But then right here, this anomalously warm water is situated at a location that is climatologically very warm. The warmest climatological signal in the world right now is over here. So now we have a warm anomaly where it's normally warm, which implies now that there's more energy available should convective activity come into this region, resulting in organization of synoptic and planetary scale subseasonal and large-scale wave events in the tropics, which can then, through their association with deep convection, force responses into the middle latitude circulation. And so right now, I would be watching this area more than the others in terms of trying to predict what are likely outcomes in the coming weeks and months. The Indian Ocean this time of year is absolutely cooler than the Western Pacific, on average. But it's anomalously warm in the middle of the basin right now and anomalously cool in the west-northwest region and the southeast. Over the last few weeks, we've had substantial cold here and warmth more up here, and the overall pattern in that area looks like what we call an Indian Ocean dipole event. So in this situation, convection rainfall this time of year is more favored over here than it is over here. But the present daily mean sea surface temperature structure doesn't really project well onto the normal Indian Ocean dipole pattern. If I look back at the monthly mean, so here's the monthly mean anomaly, this is a lot more like the normal Indian Ocean dipole pattern, with warm more back here, although it's not so warm here near the coast of Somalia as it would be on average in a strong Indian Ocean dipole event. But there is substantial cold here. The main source of this cold is enhanced trade winds in this area, enhancing the upwelling at the coast of these islands, which is driving a cold signal, which this time of year results in anomalously low convection. You've got to be careful in this part of the world, though, how you associate sea surface temperature with rainfall. Because during other times of the year, like the spring, the northern spring, cool conditions tend to be associated with regions of enhanced rainfall. So you're working with a region that in the spring is always warm enough, almost always warm enough to support deep convection. And when it rains in a region and it's controlling the fluxes in the region, the temperature has nowhere to go but down. The effect of a region of active convection then is to reduce the incoming solar radiation, enhance the mixing and surface evaporation through the wind, and and reduce the sea surface temperature associated with a rainy period. But if you drove an atmospheric model or forced an atmospheric model by an ocean, so specify the sea surface temperature, you'll find that in this part of the world, the warmer it is, the more it will rain. So there's competing factors going on here in the real world coupled system in the warm pool, which sometimes produces an opposite relationship between temperature, sea surface temperature, and rainfall. So if it's anomalously warm right here in the spring, you might guess that you might get a ridge here, trough, maybe a ridge over North America. You'll get a downstream response. But that time of year, actually, you get the opposite. Because what's actually driving the atmospheric large-scale wave is not the sea surface temperature, but the rainfall, the tropical convection. So the general overall pattern here, from here west, looks like a structure typical for El Nino. Because El Nino is usually associated with an Indian Ocean dipole this time of the year into the winter. They have an almost one-to-one correlation. On some occasions, when you don't have much of an ENSO, much of an El Nino signal, the Indian Ocean dipole will reverse phase every other year. But whenever there's a stronger El Nino signal in place, the Indian Ocean dipole almost always agrees. There's like one or two exceptions in the whole climatology when that doesn't happen. When it doesn't happen, people tend to look to the dominant signal that's there at the time and then try to assess the statistical relationship with the large-scale flow and make a seasonal prediction. And they'll tend to be wrong because the sample size of those events is so small that it's not really giving us a representative view of what we can actually expect. Okay, so that's the monthly anomaly pattern, and I want to provide a little bit of a representation of what's been going on recently in the winds. We'll look at the lower and upper tropospheric winds, how the models are projecting the patterns going forward, and then compare that first against the low frequency variability, and then look at the patterns associated with subseasonal and shorter timescale variations. So we're going to first look at, this is Kyle McCritchie's website. He was a former PhD student of mine who's now employed at the Climate Prediction Center. And the diagram, the bottom side of this longitude time diagram, with time going the right way, time's going up, that's the way physicists do it, has 850 hectopascal zonal wind anomalies here from the CFS analysis fields. The CFS forecast is going forward, and we're going to also compare that against ECMWF forecast data from here. In the low-level winds, there's been a tendency for enhanced easterlies in recent months over the Indian Ocean, enhanced easterlies over the East Pacific, which is enhancing the upwelling in that region. It's coupled to the upwelling of cold water. So the upwelling of cold water enhances the temperature differential from east to west and enhances the trade winds in response to convection driven from the Western Pacific. While over the last several months, there's been westerly wind anomalies centered in the Western Pacific, but then a kind of subseasonal event goes through and it retracts a little bit from where it was. You might really think of this eastward extension as not as representative of the base state, but instead there was an MJO event coming through here. You've got easterly phase goes from west to east around the world, followed by the westerly phase coming around. Into the early summer, we had a lot of this MJO activity, superimposed on this kind of bay state that has low-level westerlies in this area, easterlies here, and easterlies back here. But then the MJO signal after that became less dominant, and instead westward moving waves started to stand out more. These signals moving from east to west are associated with equatorial Rossby waves. Equatorial Rossby waves are forced in the tropics by breaking extratropical Rossby waves. So you get anticyclonic Rossby wave breaking across the subtropics that deposits cutoff cyclones into the subtropics, which then take on the characteristics of equatorial Rossby waves, then move to the west. Typically, they interfere with the MJO, so you see this eastward moving region of low-level westerlies, and you see the low-level westerly regions moving from east to west, embedded in the large-scale envelope, moving from west to east. But you get to this stage here, and there's still an eastward moving signal in there, but the westward moving signals are becoming more dominant. Overall, the pattern has favored westerlies in this area, and look what the model does with this now. A couple weeks ago, the model wasn't nearly as excited about the westerlies developing here, but this is like a classic Central Pacific structure El Nino pattern developing. And one reason why the models a few weeks ago weren't growing that signal as much is because we hadn't had a really strong westerly wind event. So just very recently, just the last few days, we've had actually quite an extraordinary, not particularly long lasting, but an extraordinary intensity westerly wind event. So maybe the last 5-6 days, but it's been going on for several days even before that, where there's westerlies in this region favored overall. But then this explosion of westerlies here. The wind stress on the ocean goes with the square of the wind forcing. So a more intense period of wind like this, even with a synoptic atmospheric timescale, is going to be associated with a much larger signal response in the ocean than these weaker westerlies were. And so now that the model has integrated this forcing in, it's going to grow its respective El Nino signal. You've got to be careful, though. The model, just like the model underdid the westerly event several weeks ago, projecting forward, it couldn't predict that westerly wind event very well. As the event got closer, the model started to predict it better. And then the event actually occurred, and then that forcing is now integrated into the ocean, is now forced downwelling of warm water. I'll illustrate that in a minute, what it looks like in the ocean, how a downwelling wave is forming in the ocean, which will then migrate warm water volume from west to east, pushing the thermocline down in the ocean and migrating the response eastward across the basin. But just as the model didn't predict this signal very well, it's also not predicting this signal very well. And there's a lot of uncertainty in, say, the intensity of trade wind developments along this trajectory. Ultimately, when the atmosphere forces a Kelvin wave in the ocean, that wave in the ocean is going to make a difference in the eastern basin according to its amplitude and the wind it experiences as it propagates. So like if there was no wind anomaly after the initial triggering, then the wave is just going to go across the basin and change things according to its actual initial forced amplitude. The Kelvin waves don't damp very much as they move across the basin. They're robust, one of the most robust waves in the natural world. But if this wave forced here experiences westerly wind anomalies across much of its trajectory across the basin, its effect downstream, effect farther east, is going to be amplified over time. On the other hand, if it encounters trade winds along its trajectory, then it will attenuate. And then by the time it reaches the eastern basin, it would have a smaller impact. So right now, this model at least would suggest that we've got a few weeks of amplification before the wave gets out in this area and intersects with these trade winds, which, as far as the model goes, at least this ensemble average up here, it's not a particularly intense trade wind signal that it encounters. And if that verifies like that, then this kind of growth in the bulk El Nino response pattern continues, and I would argue then that the CPC made a pretty serious error this summer in discontinuing their ENSO advisories. Even though, Nino 3-4, which is their main index, dropped off, but Nino 4, the Central Pacific, stayed high. And that could continue, it could expand to the east, it could retract, any number of things could happen. There's a lot of degrees of freedom in the system. But the CFS has kind of a bias toward over-intensifying this kind of coupling amplification. We're actually being recorded, so if you have questions, I'll repeat them in here. I'm going to use this for the forecast, subseasonal forecast.
Quick question. Did you see any similar signal in the forecast during the late spring, early summer, like maybe towards like late May?
Yeah.
Perhaps?
So he's asking if we had a similar kind of signal in the forecast going into the mid to late spring, and you can kind of see it here.
Right.
There's a westerly wind event associated with an MJO that arrived in the Central Basin, and prior to that time there may have been some evolution in the ENSO condition, but then that MJO event helped to kind of keep the warm signals in place into the summer. And so the subseasonal signal and the synoptic signal matters to the evolution of the climate signal. And this is actually a serious problem because we don't simulate the synoptic and intraseasonal signals very well. And so this is a principal reason why we don't have a good track record in predicting ENSO. We've had many instances where the forecasts have been just totally wrong based on just a shift in subseasonal variability. 2014, April, looked just like 1997 April. The ocean pattern, the subsurface pattern, virtually identical between the two. If any 2 years can be similar, they were. I'm talking just right in the tropical Pacific region, looking subsurface in the ocean. And in 1997, the westerly wind events kept going through the summer. In 2014, they ceased. And the event just kind of weakened. It stayed warm in the Central Pacific. There was warm up next to the coast of Mexico. And so we still had El Nino outcomes in the summer tropical cyclone season. But it waited until the next year before finally the force-in was able to produce another mega El Nino event. So we don't really have hope of predicting synoptic and subseasonal variability more than 6 to 8 weeks down the road if we're lucky. But if the models don't even represent the spectrum of the variability right, then it's going to miss the ensemble spreading that would result from a real world, well-represented subseasonal and synoptic signal. If you can represent the subseasonal and synoptic signals well in terms of their spectrum and when they tend to occur, their overall physics and characteristics, then you can expect that you'll be able to better assess the risk of the forcing impacts of those things on the climate. But climate models, on average, tend to keep the same ENSO state through a season. They don't do very well producing shifts in the variability in comparison with, what we might hope. They're a lot better than they used to be. In the late 1990s, I had my first look at climate model representations of ENSO. Some models didn't have it at all. Other models had this purely cyclic, like a 2-year return to El Nino or a 3-year return to El Nino, and you could set your clock by it. And the reason is that these models were dominated by the existing coupled signal so that the wave reflections from the boundaries produce like clockwork reversals in the signal. But the real world has these punctuated forcing events associated with subseasonal variability that grow or destroy El Nino events in progress. They used to call this noise. I mean, a lot of the oceanography, specialists in oceanography in ENSO call this stuff weather noise. And well, we know that the weather noise is coupled loosely to ENSO itself. So like El Nino, warm signals in a given region will favor MJO events crossing those regions to grow there. And so there's a bias in the subseasonal variability that El Nino itself produces that then can perpetuate changes in El Nino in a given direction, so that if you simulate it well, even if you might not get the timing of the MJO events 3 months down the road, if you know where the warm signal is right now, then if you simulate the MJO variability sufficiently well, I'm not talking predict it, I'm talking simulate its characteristics, then it will tend to grow in that area, even if it occurs 2 weeks or 3 weeks down the road of when you might have when you might have predicted it. But whether it occurs on June 10th or June 20th is not so important to the collective long-term variability. I mean, there is some sensitivity at some times of the year, like when monsoons are turning on and off, or right in May. There's this spring predictability barrier that a lot of people are still talking about that is associated with, it's really associated with a small difference between the absolute temperature and an El Nino temperature, because the East Pacific is at its warmest climatologically in May. So that a half a degree El Nino anomaly at that time is huge compared to a 3 degree El Nino anomaly in December. And so you can consider the effect on rainfall of the two different things. Well, the difference between El Nino and non-El Nino that time of the year represents a small adjustment in sea surface temperature. But a big subsurface anomaly in May means a thermocline, say, is pushed down. And so that when the trade winds come up in June, it's a really sensitive time to continuation of an El Nino event. So if when you're coming into June, you're in the upwelling cool phase of subseasonal variability, El Nino is less likely to stick than if you had the downwelling phase of the subseasonal variability in the Pacific. So timing matters to some degree. But when we're talking about being able to simulate risk of different outcomes in the climate models, you want to be able to predict the statistics of the subseasonal developments well, so that you could know then in your ensemble what the range of outcomes for ENSO would be. But if you don't represent the subseasonal signal properly, then you're not going to get the risk right for transitions in the low frequency variability. So this model will just kind of tend to hold this in place until the spring. That's the tendency when it gets locked in like this. But there could be a large scale pattern that shifts and produces a strong trade wind surge right in the middle of this thing and reduces its amplitude over time. So there's a sensitivity of the climate to the weather. Now that's the 850 flow. And I can also show the 200 millibar, get the upper tropospheric signal. When you have deep convection situated in the Central Pacific, you tend to have a region of easterlies extending to the east of the convection a little bit. But then a little farther east, you get westerlies. It's not that the convection is directly driving these westerlies in general. What's happening is the convection situated on the equator forces mass poleward into the subtropics and accelerates the subtropical jet stream. And it forces a Rossby wave response into the middle latitudes. And that Rossby wave response in the middle latitudes forces then a trough onto the equator well to the east of the convection, and the trough is associated with acceleration of westerlies along the equator. So if there's a large-scale wave train that's forcing this response, you'll get westerlies out here. Typically, in strong El Nino conditions, the strongest rainfall may still be near the dateline. But there's easterly wind anomalies extending in the upper troposphere most of the way across the East Pacific. It's not so much because there's convection occurring all the way. I mean, if you look where the convection is strongest, you've got easterlies to its east and westerlies to its west. But wait, doesn't that mean subsidence in the region? Well, no, because there's mass moving off the equator meridionally. So what that convection near the dateline is doing is forcing mass poleward, building the ridges north and south. But then the background westerlies advect those ridges eastward in the subtropics, which then results in easterlies on the equator through the convection. But then the wave train forces troughs onto the equator over the western hemisphere, over the Atlantic or South America or the East Pacific. In this case, it's the Eastern Pacific and South America. So you got westerlies now forced in this region. It's forcing drought in Brazil, South America, associated with an ENSO kind of forcing structure event, which is enhancing the normal summer drought. There's normally wildfires in Brazil in their dry season during northern summer. But when you add El Nino to it, it makes it worse. So we get the overall picture of what's going on here, but there's a little bit of a change in the signal right here. This region of easterlies right here is associated with ridges coming into the equator. And that advances eastward. This is taking on the characteristics of an MJO event, a Madden-Julian oscillation event. And if you look we looked at the low-level flow here, and we see there's a westerlies here, and then they advance eastward across, and they come back. But look, in the model, they don't cross, at least in the net, they don't produce a net reversal of the winds over the Indian Ocean or the Western Pacific. And reason, of course, is the basic state right now is becoming stronger than the subseasonal condition. What time do we have? 12:05. Okay. So here is the corresponding low-level wind from ECMWF data. This is provided by WSI. And we have the MJO event coming around here is associated with this intense westerly wind burst, which achieved amplitudes, at least very locally, approaching 14 meters per second. These are anomalies, they're not total winds, but this part of the West Pacific has westerly wind in the mean state this time of the year. So this is quite an extraordinary forcing event. And you'll notice just a little bit downstream, you get a swap, a little to the east now, you get a swap between the recent easterlies back to westerly anomalies in the eastern basin. This is going to reduce the amplitude of the cold anomalies in that region. This is going to go by. Now the question is, does the base state kind of pick up and maintain those westerly anomalies for longer after this MJO event goes by, and then allow the system to move toward a more canonical kind of El Nino structure over time? Or does the signal coming around the world continue to just achieve fluctuations on top of that signal? So the question is, what dominates, subseasonal or low frequency? Well, the model here, even the ECMWF, is picking up on, it's punctuated, but it's stationary, enhanced trade wind signal over the Eastern Indian Ocean. A little bit of a low-level westerly signal or near neutral over the Western Indian Ocean and East Africa. This signal is consistent with what we'd expect for a fall amplification of the Indian Ocean dipole. And if you look at the CFS rainfall data, you see just that. Same kind of thing. It's already been there a little bit, but these Indian Ocean dipole signals achieve their greatest amplitude in the fall. If you try to diagnose the Indian Ocean dipole structure in annual data, using the full seasonal cycle, the EOF representing the Indian Ocean dipole comes out second. And it doesn't really stand out from noise. And Ahmed and I had this experience with a reviewer who suggested, well, the Indian Ocean dipole isn't even real because of this. It's just not distinguishable from noise. Of course, if you repeat that analysis, including just September, October, November, December, then it comes out as the first EOF. It's the dominant signal. That's the time of year when you expect coupling between the ocean and the atmosphere in the Indian Basin, because the cold signal left behind by the previous summer's monsoon allows for this differentiation between, it's a Bjerknes feedback, wherein you get, if you get easterlies over the western Indian Ocean, it's pushing the thermocline down and now being associated with enhanced, higher temperature and enhanced rainfall. But if the same thing happened in the spring, it's just warm everywhere, and convection is going to cool the sea surface temperature more. When it's warm there this time of year, it rains. When it's warm there in the spring, it's typically dry because it's warm because it's sunny. So this kind of signal you expect to go on into December and then dissipate, but the CFS is also growing the Central Pacific convection, which would produce a downstream impact. Okay, now I want to highlight what's going on in the ocean cross-section. So we're looking at these recent westerly wind event. We want to know what's the ocean doing in response. So we're going to look at TAU buoy data from the equatorial Pacific. Now there are some missing buoys right now, some buoys that aren't reporting data, and so these data aren't as representative as we would like them to be, but it's just a good resource anyway. So we're looking here at cross sections. This is ending on September 1st, 2019, and we've got, of course, this is the thermocline right here, floating above the cold water below, so you get the warm water floating on the surface. The trade winds, normal trade winds, pile up the warm water in the west and upwell the cool water in the east. But we've got an anomalous signal superimposed on that with subsurface warmth in the Central Pacific. Now here's the most recent pentad. So that westerly wind event happened in between here and here. So what you're seeing is depression of the thermocline to the east of the westerly wind event and enhancement of the subsurface warm anomalies at the same time. But our data showed enhanced easterlies to the east of the westerly wind event. Look right here. And that is producing upwelling in the eastern basin. So now go back to this again, ending September 1st, ending yesterday. So you're seeing two things happening. One is an amplification of the subsurface anomalies, subduction of the thermocline near the dateline, and raising of the thermocline in the east. So what's going to happen over time, assuming the wind interference doesn't change the structure overall, is that this whole pattern evolves eastward. This cool anomaly shoals produces some cooling in the East Pacific. This signal continues to grow over the next couple of weeks and move to the east. So the result is a gradual transition of the system back to a little bit warmer state than we have before. I don't see any reason why this is a huge change in the system, like toward a major El Nino event formation, but there's some risk of that occurring. One event that happened this same time of the year was 1986. So you can look in the data for that time. There is no TAU data back then, but you can look at the sea surface temperature. There's very little TAU data back then, I mean. So you can look at the other data available for 1986 and see a dramatic westerly wind event that became associated with a downwelling Kelvin wave that moved slowly across the basin and phased with westerlies for most of its path and produced a large increase in the sea surface temperature through the fall and that winter that resulted in a warm anomaly that remained until the following December. So that is the subseasonal and subsurface evolution of the ocean cross-sections in response to the westerly wind event. Now I want to give you a little bit of an illustration. I think I'll zoom in on this thing. A little bit of illustration on what the pattern in tropical convection, the low frequency pattern in tropical convection, favors in terms of the upper tropospheric circulation pattern. So this is reconstructed from just patterns in the tropics only using OLR data and nothing else, and then I regress the fields of global circulation data onto that data using an algorithm I developed a couple of years ago, published in the Quarterly Journal of the Royal Meteorological Society. It's called the method of seasonally varying regression slope coefficients. So I can see how one time of year, the same signal may project a different kind of response in the global circulation than another time of the year. And this algorithm accounts for how the seasonal cycle is changing as we project forward in time lag from the original predictor. So the predictors are the first time extended EOFs, several of them, like a dozen of them, of low frequency OLR data. And the pattern is shown in the shading. The OLR pattern is shown in the shading, which has a little bit of enhanced convection located near the dateline, some region of slightly enhanced upper tropospheric easterly winds there with westerlies to the east, subsidence over Brazil, suggesting the drought that we've been talking about. And when I go forward in this thing, it's effectively a lag regression taking a correction from the seasonal evolution. So as I do this, you're going to watch the pattern change as we come into October and then November. So you see this region of upper tropospheric easterly wind near the equator and ridges over here. This is associated with the El Nino signal maintaining near the dateline. This algorithm doesn't know what's going on in the ocean. It only knows the statistics of the things going on in the OLR data.
Can you remind me what the contours represent again?
So the contours represent 200 hectopascal geopotential height anomalies.
That's right.
So we have ridge, trough, ridge, Western North America. So coming into November, the pattern suggests a cold response. Assuming this were the dominant signal at the time, that subseasonal variability remains not as strong as the base state, it would suggest a higher probability of cold conditions here averaged over the month of November, with enhanced storminess at the coast. Also, a period of enhanced wind in northern and western Europe. And this is based just on the low frequency pattern. There's no subseasonal signal in here at all. You have to keep in mind when thinking about low frequency variability and making a seasonal forecast that an extreme subseasonal event can change the seasonal mean. This is one of the biggest complications in making seasonal forecasts in any quantity. I mean, with some imagination, you think of something like predicting seasonal rainfall in Phoenix, where a synoptic event, a single thunderstorm event, can change your seasonal rainfall from below normal to above. And so in some contexts, seasonal forecasts represented by low frequency variability are better, and in other cases they're not. The Indian monsoon is not particularly good because subseasonal variability is such a strong component of outcomes there. But you still have some predictability in knowing the state of ENSO and predicting what the monsoon will do. So, but this is what the overall state would be ignoring subseasonal patterns. So you want to get a quick view of what's going on in the wind conditions, the subseasonal conditions. So I'm going to the CPC site and clicking on MJO and then coming down. And I'm looking at the map. So the total flow, you can see the overall monsoon circulation is still in place, but beginning to retreat southward. The trade winds are dominant in this area. There's a monsoon region westerlies in the East Pacific. The anomalous pattern would suggest that this is an anomaly that was subseasonal. It disappears and reverses here as the large-scale state changes. There's a large-scale wave train in the southern hemisphere right now that's propagating across this way to the Atlantic region and toward the equator. I'm going to check again how much time I have. So we've got about 10 to 12 minutes. So the wave coming this way adjusts the wind patterns in the tropics across the western hemisphere because the waves break into the tropics and then influence the momentum there. This is low-level wind. And then we can look at the corresponding upper level wind and the wind anomalies. So a part of the upper level wind signal here is associated with the large scale base state. Tendency for easterlies here is base state. Tendency for westerlies here is also base state. But then there's a large scale wave pattern that has waves coming into the equator over here and that are enhancing easterlies in the upper troposphere of Africa and the Southwest Indian Ocean. This pattern of approach of easterlies into that region from the extratropics and also across the tropics is consistent with evolution across the Western Hemisphere MJO phases and toward the Indian Ocean phases. I'll show you some more specifics of what that actually looks like seasonally this time of year in a moment. I want to look at the condition of the Wheeler and Hendon RMM indexes right now. I would argue that these are not the best tracer right now of subseasonal variability in the tropics because there's been a lot of these westward moving waves that are standing out. And so you're going to miss a lot of the variance if you just focus on this thing. But nevertheless, it's useful to know where we are right now. And right now, the base condition is crossing the West Pacific. It's within the circle, but there is a large-scale convective anomaly. So we saw that westerly wind burst in the West Pacific just recently. Westerly wind bursts like that are associated with then northward moving regions of active convection that cross the West Pacific. I can show in the model data, so you can get a view of that northward propagating feature over the next couple of weeks. You see right now the active convection is situated here. You go forward in time and it shifts to the north in the model. So the westerly wind burst began on the equator and then evolves poleward and westward. And so you'd expect that the large-scale response patterns are going to evolve as forced by this thing, even if the index itself goes into the circle. But then I mentioned that evolution of those southern hemisphere wave patterns that are projecting ridges toward the equator over Africa and the Indian Ocean. Those things accelerate the upper tropospheric easterly wind and produce divergence of mass over the Indian Ocean warm pool and ultimately move the signal back to this area. So this is what's motivating the mechanism, motivating the propagation of this signal around the world is facilitated by those southern hemisphere wave patterns this time of the year. You move more into our winter and you look more at the northern hemisphere wave train patterns coming around the world. So the MJO signal in the tropics, which we normally consider a tropical mode, is not independent from the evolution of the mid-latitude flow. That the mid-latitude flow is one of the major factors that influences the propagation of the convection. And then that takes energy from the convection as well, leading to downstream impacts. So this is the European Center Monthly. This is a bias-corrected version of the thing. It takes a very long time sitting in these phases. So I'm going to give you a quick demonstration of what to expect given the evolution of the MJO signals over the West Pacific that way. This is including just MJO, not equatorial Rossby wave signals, just MJO. When I include the equatorial Rossby wave, it becomes a little bit more complicated. So going forward here, this is the same kind of prediction that I just showed you with the low frequency variability. This is MJO only though. Going forward, ridge, eastern North America. There's a pattern of ridge south of Alaska, trough in western North America, and a ridge in the eastern United States. And in fact, you can compare that against the geopotential height anomaly patterns in the ECMWF. Find that there's quite a lot of variance over these next few days that's pretty well explained by that structure. But the timing of the loss of the signal here, it holds on a lot longer in here before reversing and coming to this pattern given MJO only. I have another product I'm not going to have time to show you today that uses the equatorial Rossby wave in addition to the MJO, which has a more similar evolution to the ECMWF prediction, but then is able to extend forward to suggest when transitions will occur. But even ignoring the equatorial Rossby wave pattern, just taking the MJO signal by itself, there's a pretty high probability of a cold event developing across October in the eastern United States. And so we go from a warm scenario in the western hemisphere phases, but when the MJO comes back toward the maritime continent and West Pacific regions coming into that time of year, the response pattern reverses. So finally, I'm going to illustrate that here using this climatological normal, let's see, minus, I'm going to shrink this down so we can see the whole thing. Climatological normal for time of the year. I swipe left and right, and that's day of year. And I swipe up and down, and that's the RMM phases. And these are the average this is the expectation value that you might expect the 200 millibar geopotential height and wind patterns to follow given that kind of MJO evolution. In the middle of September, being in phases 6 and 7 is associated with a warm anomaly. But moving further into the year, toward the end of September and into October, look what phase 8 does. Phase 8 used to be cold. Phase 8 becomes warm. So when you're at this time of year and you start in phase 6 and you end in phases 8, 1, and 2, because I go further forward here, 1 and 2, phases 8, 1, and 2 become the warm phases when they used to be the cold phases. Phase 6 was the warm phase. So now you start in the warm phase in phase 6 in middle October, or September, and then move forward into October into the later phases. It tends to lead toward an extended warm period. But then when you then go beyond that, you start going into phase 3, 4, 5. So this is where that cold outcome we were talking about emerges, when the next MJO signal comes back toward the Pacific Ocean. Then what was once warm in the Pacific is now cold. And I think we're running out of time here. Are there any comments or questions this so far? We won't do this presentation every week, but I plan on doing it whenever there isn't a student presentation or some other conflict going on. Good.
I have a general question. Is there a need for a more objective criteria for various ENSO states when we're characterizing MJO response?
Yes. So I'm trying, this product right here, this one, isn't just using the MJO state by itself. It's not using the RMM index. It's using a set of structure patterns, time extended EOFs, that get the structure better than the RMM index does. But then I modulate that regression by the background wind in the tropics, which takes into account the ENSO condition. So this is a modulated MJO forecast. I have another one that's not. This is a product that's based on just the average MJO condition. And it evolves in this case pretty much the same, because it turns out that the average MJO condition is pretty similar to what you can expect to get in the present base state. But that's not always true. This is an important point. I think we need to move out to let the others in. Thank you.